To administer Oracle database and keep it running smoothly, the database administrator, DBA, must regularly monitor its performance to locate bottlenecks and to correct problem areas. A DBA can look at hundreds of performance measurements, covering everything from network performance and disk input, output, I/O, speed to the time spent working on individual application operations. These performance measurements are commonly referred to as database metrics. You can respond to changes in performance only if you know the performance has changed. Oracle Database provides several ways to monitor the current performance of the database instance. The database homepage of Enterprise Manager Database Express provides a quick check of the health of the instance and the server, with graphs showing CPU usage, active sessions, memory and data storage usage. The homepage also shows any alerts that have been triggered. Additional detail is available on the Performance Hub page. This page will be reviewed later in the lesson. The information displayed in Enterprise Manager is based on performance views that exist in the database. You can access these views directly with SQL+. Occasionally, you may need to access these views for some detail about the raw statistics. The three facets of tuning involve performance planning, instance tuning, and SQL tuning. Performance planning is the process of establishing the environment, the hardware, software, operating system, network infrastructure, and so on. Instance tuning is the actual adjustment of Oracle database parameters and operating system, OS, parameters to gain better performance of the Oracle database. SQL tuning involves making your application submit efficient SQL statements. SQL tuning is performed for the application as a whole, as well as for individual statements. At the application level, you want to be sure that different parts of the application are taking advantage of each other's work and are not competing for resources unnecessarily. There are many facets to performance planning. Planning must include a balance between performance, speed, cost, and reliability. You must consider the investment in your system architecture, the hardware and software infrastructure needed to meet your requirements. This, of course, requires analysis to determine the value for your given environment, application, and performance requirements. For example, the number of hard drives and controllers has an impact on the speed of data access. The ability of an application to scale is also important. This means that you are able to handle more and more users, clients, sessions, or transactions, without incurring a huge impact on overall system performance. The most obvious violator of scalability is serializing operations among users. If all users go through a single path one at a time, then as more users are among users. If all users go through a single path one at a time, then, as more users are added, there are definitely adverse effects on performance. This is because more and more users line up to go through that path. Poorly written SQL also affects scalability. It requires many users to wait for inefficient SQL to complete, each user competing with the other on a large number of resources that they are not actually in need of. At the start of any tuning activity, it is necessary to have specific goals. A goal, such as process 500 sales transactions per minute, is easier to work toward than one that says, make it go as fast as you can, and we'll know when it's good enough. You must allocate Oracle database memory suitably for your application to attain optimum performance. You have a finite amount of memory to work with. Too little memory allotted to certain parts of the Oracle database server can cause inefficient background activity, which you may not even be aware of without doing some analysis. Oracle has developed a tuning methodology based on years of experience. The basic steps are: 1. Check the OS statistics and general machine health before tuning the instance to be sure that the problem is in the database. Use the Enterprise Manager Database homepage. 2. Tune from the top down. Start with the design, then the application, and then the instance. For example, try to eliminate the full table scans that cause the I/O contention before tuning the tablespace layout on disk. This activity often requires access to the application code. 3. Tune the area with the greatest potential benefit. The tuning methodology presented in this course is simple. Identify the biggest bottleneck and tune it. Repeat this step. All the various tuning tools have some way to identify the SQL statements, resource contention, or services that are taking the most time. The Oracle database provides a time model and metrics to automate the process of identifying bottlenecks. The advisors available in Oracle database use this methodology. 4. Stop tuning when you meet your goal. This step implies that you set tuning goals. This is a general approach to tuning the database instance and may require multiple passes. The Oracle database server software captures information about its own operation. 3 major types of data are collected: cumulative statistics, metrics, and sampled statistics. Cumulative statistics are counts and timing information of a variety of events that occur in the database server. Some are quite important, such as buffer busy waits. Others have little impact on tuning, such as index block split. The most important events for tuning are usually the ones showing the greatest cumulative time values. The statistics in Oracle database are correlated by the use of a time model. The time model statistics are based on a percentage of DB time, giving them a common basis for comparison. Metrics are statistic counts per unit. The unit could be time, such as seconds, transaction, or session. Metrics provide a base to proactively monitor performance. You can set thresholds on a metric, causing an alert to be generated. For example, you can set thresholds for when the reads per millisecond exceed a previously recorded peak value or when the archive log area is 95% full. Sampled statistics are gathered automatically when statistics underscore level is set to typical or all. Sampled statistics allow you to look back in time. You can view session and system statistics that were gathered in the past, in various dimensions, even if you had not thought of specifying data collection for these beforehand. You can access the Performance Hub page from the Performance menu. On the Performance Hub page, you can view all the performance data available for a specified time period. You can choose to view real-time data or historical data. More granular data is shown when you choose real-time data. When you view historical data, the data points are averaged out to the Automatic Workload Repository, AWR, interval, usually an hour. Different tabs are available on the Performance Hub page based on whether you choose real-time or historical data. You can also use Enterprise Manager Cloud Control to manage the performance of your database. Access the Performance Home page by selecting Performance Home from the Performance menu. The Performance Home page provides an overall view of the performance statistics for your database. You can use the information on this page to determine whether resources need to be added or redistributed. Enterprise Manager Cloud Control provides session detail pages so that you can view the wait events occurring in individual sessions. Select Top Activity in the Performance menu to view the summary of all sessions. On the lower right corner of the Top Activity page is a list of Copyright 2014, Oracle and/or its affiliates. All rights reserved. The top sessions. Click the session identifier to view the session details page. The Top Activity page and session details page are based on performance views in the database. At the bottom of the Top Activity page, click Top Consumers in the Additional Monitoring Links section to access the Top Consumers page. The Top Consumers Overview page shows in graphical format, top services, top modules, by service, top actions, by service and module, top clients. On the Top Consumers page, click the Top Sessions tab to see critical statistics of the sessions that are using the most resources: CPU, PGA memory, logical reads, physical read, hard parse count, sort count. Click a column name to have the results sorted by the value in that column. You can display current session information for each user logged on by querying $session. For example, you can use $session to determine whether a session represents a user session, or was created by a database server process, background. You can query either $session or $session_wait to determine the resources or events for which active sessions are waiting. You can view user session statistics in $sestat. The $session_event view lists information about waits for an event by a session. Cumulative values for instance statistics are generally available through dynamic performance views, such as $sestat and $systat. Note that the cumulative values in dynamic views are reset when the database instance is shut down. The $mystat view displays the statistics of the current session. You can also query $sesmetric to display the performance metric values for all active sessions. This view lists performance metrics, such as CPU usage, number of physical reads, number of hard parses, and the logical read ratio. In multi-TA systems where there is an application server that is pooling database connections, viewing sessions may not provide the information that you need to analyze performance. Grouping sessions into service names enables you to monitor performance more accurately. Regardless of the session that was used for a particular request, if it connected via one of these services, the performance data of the session is captured under that service name. In an N-tier environment where there is an application server that is pooling database connections, viewing sessions may not provide the information you need to analyze performance. Grouping sessions into service names enables you to monitor performance more accurately. These two views provide the same information that their like-named session counterparts provide, except that the information is presented at the service level rather than at the session level. v$service_weight_class shows weight statistics for each service, broken down by weight class. v$service_event shows the same information as v$service_weight_class, except that it is further broken down by event ID. You can access detailed information on weights from the average active sessions graph on the performance homepage. When you drill down to a particular weight category, you can view details of specific 5-minute intervals and also see the top working sequel and the top working sessions associated with that particular weight event during that time. This enables you to perform after-the-fact analysis of system slowdowns and determine potential causes. Wait events are statistics that are incremented by a server process or thread to indicate that it had to wait for an event to complete before being able to continue processing. Wait event data reveals various symptoms of problems that might be impacting performance, such as latch contention, buffer contention, and I/O contention. Remember that these are only symptoms of problems, not the actual causes. Wait events are grouped into classes. The wait event classes include administrative, application, cluster, commit, concurrency, configuration, idle, network, other, scheduler, system I/O, and user I/O. Because there is a finite amount of memory available on a database server and thus, on an Oracle database instance, you must pay attention to how memory is allocated. If too much memory is allowed to be used by a particular area that does not need it, other areas may not function properly because of lack of memory. With the ability to have memory allocation automatically determined and maintained for you, the task is simplified greatly. But even automatically tuned memory needs to be monitored for optimization and may need to be manually configured to some extent. Oracle Database enables you to specify the total memory allocated to the instance. Memory will be dynamically reallocated between the System Global Area, SGA, and Program Global Area, PGA, as needed. This method is called Automatic Memory Management, AMM, and is available on only those platforms that support dynamic release of memory. This simplifies your memory management tasks. Memory advisors are available to help you set the initialization parameters on various levels. The advisor available depends on the level on which you are specifying the memory parameters. If you enable AMM, only the memory size advisor is available. If possible, it is best to fit the SGA into physical memory, which provides the fastest access. Even though the OS may provide additional virtual memory, this memory, by its nature, can often be swapped out to disk. On some platforms, you can use the lock_SGA initialization parameter to lock the SGA into physical memory. This parameter cannot be used in conjunction with AMM or ASMM. When a SQL statement executes, data blocks are requested for reading or writing, or both. This is considered a logical I/O as the block is requested. The block is checked to see whether it already exists in memory. If it is not in memory, it is read from disk, which is called a physical I/O when the block is found in memory. The cost is several orders of magnitude less than the cost of reading the block from disk. The size of the SGA components in less than the cost of reading the block from disk. The size of the SGA components in combination with the workload has a large effect on the number of physical reads. A simple view of this implies that you should increase the memory for the SGA components as much as possible. A larger SGA is not always better. There is a point where adding more memory yields diminishing returns. This principle applies to the buffer cache, the shared pool, and other SGA components. In practice, you find that shifting memory from one SGA component to another may increase overall performance, without changing the total amount of memory given to the SGA depending on the characteristics of the workload given to the SGA depending on the characteristics of the workload. Automatic Memory Management, AMM, allows the Oracle Database Server to manage SGA memory and instance PGA memory sizing automatically. To do so, on most platforms, you set only a target memory size initialization parameter, memory_target, and a maximum copyright 2014, Oracle and/or its affiliates. All rights reserved. Memory size initialization parameter, memory_max_target, and the database server dynamically exchanges memory between the SGA and the instance PGA as needed to meet processing demands. With this memory management method, the database server also dynamically tunes the sizes of the individual SGA components and the sizes of the individual PGAs. The graphic in the slide shows you the memory initialization parameters hierarchy. Although you have to set only memory_target to trigger automatic memory management, you still have the ability to set lower bound values for various caches. Therefore, if the child parameters are user set, They are the minimum values below which the Oracle database server will not autotune that component. If SGA_target and PGA_aggregate_target are set to a non-zero value, they are considered to be the minimum values for the sizes of the SGA and the PGA, respectively. Memory_target can take values from SGA_target plus PGA_aggregate_target to memory_max_size. If SGA_target is set, the database server autotunes only the sizes of the is set. The database server autotunes only the sizes of the subcomponents of the SGA. PGA is autotuned independent of whether it is explicitly set or not. However, the whole SGA_target, and the PGA_aggregate_target, are not autotuned, that is, do not grow or shrink automatically. If you did not enable Automatic Memory Management, AMM, when you configured your database, you can enable it by performing the following steps. 1. Click Advisors Home in the Performance menu. 2. Select Memory Advisors in the Advisors region. 2. Click Enable for Automatic Memory Management. 3. The Enable Automatic Memory Management page appears. Set the values for total memory size and maximum memory size for Automatic Memory Management. Note: if you change the maximum memory size, the database instance must be restarted. 4. Click OK. After Automatic Memory Management is enabled, you can see the graphical representation of the history of your memory size components in the Allocation History section of the Memory Advisors page. The top portion in the first histogram is tunable PGA only and the lower portion is all of SGA. Additional data is available on the page showing the SGA components history and a graphical representation of the SGA allocation. On this page, you can also access the Memory Target Advisor by clicking the Advice button. This advisor gives you the possible DB time improvement for various total memory sizes. The V$memory_dynamic_components dynamic performance view shows the current sizes of all dynamically tuned memory components, including the total sizes of the SGA and instance PGA. The V$memory_target_advice view provides tuning advice for the memory_target initialization parameter. In the V$memory_target_advice view, the row with the memory_size_factor of 1 shows the current size of memory, as set by the memory_target initialization parameter, and the amount of DB time required to complete the current workload. In previous and subsequent rows, the results show several alternative memory_target sizes. For each alternative size, the database server shows the size factor, the multiple of the current size, and the estimated DB time to complete the current workload if the estimated DB time to complete the current workload if the memory_target parameter were changed to the alternative size. Notice that for a total memory size smaller than the current memory_target size, the estimated DB time increases. If AMM does not work for you, because you need a fixed PGA, consider the use of Automatic Shared Memory Management, ASMM, which simplifies SGA memory management. You specify the total amount of SGA memory available to an instance by using the SGA_target initialization parameter, and Oracle Database Server automatically distributes this memory among the various SGA components to ensure the most effective memory utilization. For example, in a system that runs large online transactional processing, OLTP, jobs during the day, requiring a large buffer cache, and runs parallel batch jobs at night, requiring a large value for the large pool, you would have to simultaneously configure both the buffer cache and the large pool to accommodate your peak requirements. Automatic Shared Memory Management is automatically enabled if you have enabled AMM. If you have not enabled AMM or did not enable ASMM when you configured your database, you can enable Automatic Shared Memory Management by performing the following steps. 1. Select Memory Advisors in the Performance menu. 2. The Memory Advisors page appears. Scroll down to the SGA section. Click Enable for Automatic Shared Memory Management. 3. The Enable Automatic Shared Memory Management page appears. Specify the total SGA size. Click OK. You can increase the total SGA size at a later time by increasing the value of the total SGA size field or the SGA_target initialization parameter. However, you cannot set it higher than the value specified by the maximum SGA size field or the SGA_max_size parameter. The Automatic Shared Memory Management feature uses the SGA memory broker that is implemented by two background processes, Manageability Monitor, MMON, and Memory Manager, MMAN. Statistics and memory advisory data are periodically captured in memory by MMON. MMAN coordinates the sizing of the memory components according to MMON decisions. The SGA memory broker keeps track of the sizes of the components and pending resize operations. The SGA memory broker observes the system and workload in order to determine the ideal distribution of memory. It performs this check every few minutes so that memory can always be present where needed. In the absence of automatic shared memory management, components had to be sized to anticipate their individual worst components had to be sized to anticipate their individual worst case memory requirements. Before enabling ASMM, you should remove the individual memory area parameters from the SPFILE because having them set can impose restrictions on ASMM. After ASMM is enabled, the SGA size advisor is available to help you choose the best value for total SGA size. If after seeing the effects of the ASMM allocations you decide that you want to adjust certain component allocations, you can specify values for those components. If the values you are specifying are lower than the current values, those values are treated as minimum memory sizes for their respective components. If the values you are specifying are larger than the current values, the sizes of the memory components are resized upward to the values you provided as long as free memory is available. Setting limits reduces the amount of memory available for automatic adjustment, but the capability is available and can help overall available for automatic adjustment, but the capability is available and can help overall performance. The procedure for enabling ASMM differs depending on whether you are changing to ASMM from manual shared memory management or from automatic memory management. To change to ASMM from manual shared memory management, 1. Get a value for SGA_target. Select sum value from $SGA. Select current_size from $SGA_dynamic_free_memory, SGA_target, from dual. 2. Use that value to set SGA_target. 3. Set the values of the automatically sized SGA components to 0. To switch to ASMM from automatic memory management, 1. Set the memory_target initialization parameter to 0. 2. Set the values of the automatically sized SGA components to 0. You can dynamically choose to disable automatic shared memory management by setting SGA_target to 0. In this case, the values of all the auto-tuned parameters are set to the current sizes of the corresponding components, even if the user had earlier specified a different non-zero value for an auto-tuned parameter. In the example in the slide, the value of SGA_target is 8 GB and the value of shared_pool_size is 1 GB. If the system has internally adjusted the size of the shared pool component to 2 GB, setting SGA_target to 0 results in shared_pool_size being set to 2 GB, thereby overriding the original user-specified value. When you specify a non-zero value for SGA_target and do not specify a value for an auto-tuned SGA parameter, the value of the auto-tuned SGA parameters in the $parameter view is 0, and the value of the ISDEFAULT column is true. If you have specified a value for any of the auto-tuned SGA parameters, the value that is displayed when you query $parameter is the value that you specified for the parameter. The Program Global Area, PGA, is a memory region that contains data and control information for a server process. It is non-shared memory created by the Oracle server when a server process is started. Access to it is exclusive to that server process. The total PGA memory allocated by all server processes attached to an Oracle instance is also referred to as the aggregated PGA memory allocated by the instance. Part of the PGA can be located in the SGA when using shared servers. Statistics must be available for the effective diagnosis of performance problems. The Oracle server generates many types of statistics for different levels of granularity. At the system-wide, session, and service levels, both wait events and accumulated statistics are computed. In the slide, the top row of views shows the cumulative statistics. The bottom row shows the wait event views. When analyzing a performance problem in any of these scopes, you typically look at the change in statistics, delta value, over the period of time you are interested in. All the possible wait events are cataloged in the $event_name view. All statistics are cataloged in the $statname view. Approximately 480 statistics are available in Oracle database. In the slide, some of the views that can help you determine the cause of performance problems or analyze the current status of your database are listed.